Imagine placing a compass beside a wire. The needle sits still. Then you switch on a current, and the needle turns. Now imagine moving a magnet through a coil of wire. A current appears, even though no battery is attached. Finally, look at a beam of sunlight. These seem like three separate subjects: electricity, magnetism, and optics. James Clerk Maxwell showed that they are three aspects of one physical structure. Even more remarkably, his equations did not merely describe light. They predicted what light is. By the middle of the 19th century, physicists had accumulated a brilliant but untidy collection of laws. Electric charges attracted and repelled. Currents deflected compass needles. Magnets produced invisible patterns around themselves. Michael Faraday had shown that a changing magnetic environment could induce an electric current. Each result worked, but the whole picture had not yet been assembled. Maxwell's achievement was not the invention of every ingredient. It was the unification of them. He took Faraday's physical idea of lines of force seriously, translated the known experiments into mathematics, and discovered the missing term that made the theory complete. The familiar four equations shown today are the later, compact vector form of a theory that Maxwell originally expressed in a much larger system. The first equation is Gauss's law for electricity. In modern notation, the divergence of the electric field equals charge density divided by epsilon naught. Its meaning is wonderfully visual. Positive electric charge acts as a source from which electric field lines spread, negative charge acts as a sink into which they converge. Place a positive and negative charge together, and the lines run from one to the other. The equation tells us how the local pattern of the electric field is tied to the distribution of charge. The second equation looks similar, but its right-hand side is zero. The divergence of the magnetic field is zero. Electric field lines may begin and end on charges, but magnetic field lines do not have observed beginnings or endings. Cut a bar magnet in half and you do not isolate a north pole from a south pole. You obtain two smaller magnets, each with both poles. Magnetic field lines form closed loops. In modern language, no magnetic monopole has yet been observed. Those first two equations describe where fields spread out or converge. The next two describe curl, how fields circulate. Faraday's law says that a changing magnetic field produces a circulating electric field. Move a magnet through a coil, and the magnetic flux through the coil changes. The induced electric field drives charges around the wire, producing a measurable current. This is the principle behind generators. Mechanical motion changes the magnetic environment, the induced electric field then moves electric charge. The minus sign records Lenz's law, the induced effect opposes the change that produced it. Now we reach the decisive equation. Ampère had connected electric current with circulating magnetism. A current in a wire creates magnetic field loops around the wire. But in its original form, the law contained a serious puzzle. Picture a capacitor, two conducting plates separated by an insulating gap. While the capacitor is charging, current flows through the wire towards one plate and away from the other. Around the wire, Ampère's law predicts a magnetic field. But no charge crosses the insulating gap. If you stretch one imaginary surface across the wire, it encloses current. Stretch another surface between the plates, and it encloses no conduction current. The predicted magnetic field appears to depend on which surface you choose. Nature cannot contradict itself because we chose a different mathematical surface. Maxwell supplied the missing piece. A changing electric field also contributes to a circulating magnetic field. Between the charging plates, the electric field is changing, and that change plays precisely the role required to preserve continuity. Maxwell called the corresponding quantity displacement current. It is not ordinary charge flowing through the insulating gap. It is the time-varying electric field completing the magnetic law. In modern notation, the curl of B equals mu naught times the current density, plus mu naught epsilon naught times the rate of change of E. That final term is the hinge of the entire unification. Now remove the charges, wires, magnets, and capacitor. Consider empty space. Faraday's law still says that a changing magnetic field curls an electric field. Maxwell's completed law says that a changing electric field curls a magnetic field. Each changing field can therefore sustain the other. The equations admit a self-propagating disturbance, an electromagnetic wave. Take the curl of Faraday's law and substitute the Ampère-Maxwell law. The result is a wave equation for the electric field. The same reasoning gives a wave equation for the magnetic field. Its predicted speed is 1 divided by the square root of mu naught times epsilon naught. Those constants came from electrical and magnetic measurements. Yet when Maxwell evaluated their combination, the result matched the known speed of light. This was the revelation. Maxwell wrote that the agreement seemed to show that light itself is an electromagnetic disturbance propagated through the field according to electromagnetic laws. Optics was no longer a separate island. Light belonged to the same theory as batteries, magnets, currents, and induction. What does such a wave look like? Choose the direction of travel as the horizontal axis. The electric field oscillates in one transverse direction. The magnetic field oscillates at right angles to both the electric field and the direction of travel. The two fields are in phase, their crests advance together. Neither points along the direction in which the wave travels. The wave transports energy and momentum through space. Visible light is only a narrow band of this family. Decrease the frequency and the same equations describe infrared, microwaves, and radio waves. Increase it and they describe ultraviolet, X-rays, and gamma rays. The categories differ in frequency and wavelength, not in their basic electromagnetic nature. In vacuum, they all travel at the same speed, c. Maxwell's conclusion began as a mathematical prediction grounded in experiment. Heinrich Hertz later generated and detected electromagnetic waves in the laboratory, showing reflection and interference behaviors analogous to light. What had emerged from the equations could be made, transmitted, and received. There is a useful philosophical lesson here. The equations do not manufacture reality, they express an intelligible order already present in nature. Their power comes from identifying a common formal structure across apparently different effects. One must still distinguish a mathematical description from an efficient physical cause. Yet a sound description can reveal unity, the same relations that govern a coil and a capacitor also govern starlight crossing space. So the four equations tell one connected story. Charge is associated with the divergence of the electric field. Magnetic field lines close upon themselves. A changing magnetic field produces a circulating electric field. Currents and changing electric fields produce a circulating magnetic field. Join the last two together in empty space, and a wave becomes possible. Its speed is c. That wave is light. Maxwell unified electricity, magnetism, and optics without reducing the achievement to a slogan. He found the mathematical relations by which each part belongs to a coherent whole. Those relations still support radio, electrical power, wireless communication, radar, and much of modern physics. For compact equations, one electromagnetic field, and a beam of light finally understood as part of the same order as a current in a wire.